Now, to model the pipeline with its fittings, what we're going to do is we're going to break down that line into a few sections. As you can see here from the diagram, we've got the water storage tank and the heat exchanger. So in between those two unit operations, there will be a small section of pipe before we have a isolation valve. I just randomly chose 1 meter. In the HYSYS model, we'll have a 1 meter section of pipe. And then soon after that, we'll have an isolation valve, which is a ball valve. And then we'll have another section that runs about 174 meters. And then at the end of that 174 meters, we'll have the flow meter. And then we'll have another section that runs 174 meters up until the final isolation valve for the heat exchanger. And then from that valve, we'll have a small spool that connects the ball valve to the heat exchanger, right? By breaking it down into these sections, you will be able to see the pressure drop due to this valve here, the pressure drop due to this flow meter, and the pressure drop due to storage tank isolation valve. You might have to pause and come back to this sketch. So from the HYSYS model, what I need you to take out of that is how quickly you can be able to insert all this equipment or these fittings into the model. Okay, now let's jump over to HYSYS and then continue with the problem. Okay, now we are here in HYSYS. I'll tidy up this flow sheet here. I'll just right click on the pipe icon there, bring out this table or show table. And what I want to see here is just the pressure drop, the overall pressure drop. So I'm going to control select all and then remove all these variables. And from there, I'll come back here and then add the overall pressure drop. There it is there. And yeah, so you can see from this table, we've got just the overall pressure drop. You can insert any variable that you like as long as it is within the pipe segment. For example, I will add the temperature. There's the feed temperature there. And I will add the product temperature. There you go, product temperature. And you'll have those in the table. So you can see the feed temperature will be the same as the temperature that's coming in with the feed water. And the product temperature will be the outlet temperature, which is the same as the exit temperature as we have there. That's just cosmetics of the flow sheet. Now let's go into the pipe segment itself and then start to insert those fittings we spoke about. To do that, you double click on the pipe segment icon there and we resize this window. We inserted all these pipe geometries from the previous video. I need you to look very closely to what I'm going to be doing now, because this method that I use here will cut your time by half, if not by 80%, and make you more efficient and quick in doing your pipeline segment simulations. If you remember, we've put in this piping geometry from our first video. If you remember from the sketch, we had the tank. And then from the tank, we had our first section of the line was 1 meter pipe. So I'm going to just change the length of this pipe to 1 meter to represent that section of pipe. And then the increments, I'm just going to use 2 increments. So breaking that 1 meter section of pipe into 2 segments, right? And then from there, I want to add a ball valve. Now, how do I do that? What I'll do, you just come here, you hover over the append segment. It says add new segment at the end of the pipe, right? So that's the one that you need. You add. Now we've got a segment that is added at the end of that 1 meter pipe, but it's not really a pipe. We want a ball valve. So on the drop down there, you come and get a ball valve fully open. The ball valve, we're assuming it is a full ball valve, which will have the same internal diameter as the pipe. And then you've got a green bar there. That means we have modeled now that 1 meter pipe and a ball valve. And at the end of the ball valve, we want to have that 174 meter pipe run. And to do that, you don't have to do anything fancy here. You just come here, you clone this one, because this is just a pipe, right? This is a 1 meter pipe, but you want to have a similar pipe with the same dimension. So you come here, you just click on that one at the top and you say clone. It will put another section of pipe after the valve. So clone. Then there's your segment 3, which is a pipe, but it's 1 meter. No, we don't want 1 meter, we want 174 meters. And then by just doing that, you have done those 3 elements of the pipe section. And then after the 174 meter line, we had the flow meter. Now we want to insert the flow meter here, right? So I'll click on this fitting here, this ball valve. I'm going to clone the ball valve, but later change it to a flow meter. And this is how you do it. You just click there and then click clone segment, and then it attaches the ball valve after the 174 meter line. But we want this to be a water meter turbine type. And then you just change it, and then you assume that it's also a full bore turbine, which is 52.5 millimeters. Then you got a green bar there. So by just doing that, you have modeled the pipe, the valve, the pipe, and the flow meter. What is left is just that 174 meter section of line going towards the heat exchanger now. To do that, I'll just click on this section. That's the one that I want to clone. I click on it and say clone, and then it attaches there after the flow meter. And that's pretty much it. The last section that you need to do is, the last 2 sections, is you've got the 174 meter pipe. Now you need to have the isolation valve towards the heat exchanger. You click on this, you clone it. Boom, then you got your ball valve inserted, and you don't need to do anything else. I find this to be very quick. You don't have to be repeating your actions again and again, as long as you understand the clone, insert, and append part of it. And then the last section is the 1 meter line that attaches to the heat exchanger. I'll click on the pipe, and then I'll say clone, and I'll have it. Oh, no, it didn't work. No, that didn't work. But anyway, that's fine. I'm going to delete this. I click on it, delete. What I want to clone is this here. I click on it and then say clone. There you go. That's what we want to see. And then your line is pretty much done. There's only one thing that I forgot to update. You see how we've got this 174 meters in 2 sections? I would really like to make that to be maybe 10 sections, so it's more granular. 174, 10 sections, that's about right. I would change that as well to make it 10 sections or 10 increments. Yeah. And that's it. So you have pretty much modeled the fittings on this line. Now let's go to the performance tab to see what pressure drops these fittings imposing on our system. You come to the performance tab, and then you see the total length is still 350 meters. It's just that we just broke it down into smaller sections. And then these are your results, similar to our previous video. So you will see where we have the fittings, which are not pipes. You will see the heat transfer here is 0. Wherever you see this, you know that this is the fittings. This would be the first isolation valve from the tank, and then this would be the flow meter, and this would be the last isolation valve. So these are our fittings. And then you can come here and look at the pressure drops across those fittings. You can see that the pressure drop at the first valve is only 0.1 kPa. What I've done in the background, I've checked myself, and I did calculate the pressure drop across a typical ball valve, and this is bang on 0.1 kPa. You can go and double check me, but I'm pretty sure you'll get a 0.1 kPa if you're using the same velocity, which is 1.927 meters per second, and you are also using a density of water, and the K value, I think it's 0.05. So if you're using the K value method, or you can also use the equivalent length method. So we've got this pressure drop across that valve. I would expect to have the same pressure drop across the other isolation valve. See that? These two matches up, so they show me that this is the same fitting. But the biggest pressure drop is coming off from that flow meter. In the middle of the line, it's got about 11 kPa. In this way, you can quickly see how much each fittings is contributing towards your overall pressure drop. How cool is that? And then the last thing you can do, you can also view this on a graph for reporting purposes. You go to your plots. So you see the line at 0 meters, you start with 1000 kPa, and then it drops linearly as it goes towards the 350 meters. But you can see here, there's a kink here. This kink is where we have our flow meter, which has got about 11 kPa pressure drop. You can see if you hover over that point there, which is 855, and I will expect this to be about 866, which is pretty much about 11 kPa pressure drop. The two valves, which are somewhere here and there, the pressure drop is so small, it's 0.1. You might not be able to see it on this scale, but it is there. At 1 meter, if you can go to, don't even have the resolution. That pressure drop of 0.1 on this scale, you might not be able to see it fully, but this is the graph that you use to look at the profiles. I hope that helps. If there's anything that you missed or you reckon I might have glanced through, you're more than welcome to send me an email, and then I will try my best to respond to your question. Great. This concludes our video for today. And I hope from this video you were able to grasp the basics of how to model a simple pipe and how to view the results in both table and chart format, and how to insert the fittings into the pipe segment. And I hope you also learned how to evaluate pressure drop imposed by each fittings in the system. One other thing that I didn't mention is the heat loss. You can also see how much heat was lost from the pipe, as I have it there in the table. One quickest way to do that is just to click on this energy stream, and you can see that the heat flow is 10.8 kilowatts energy that was lost. Okay, thank you so much for your time, and I'll see you in the next video.